Welcome to The Explainer. Today we're diving straight into the invisible digital armor keeping our modern power grids alive. You flip a switch, the lights come on, but the math and modeling making that happen, it's absolutely wild. So let's get into the source material and see how it all starts in a virtual world.
So here's the big question. How do we actually keep these incredibly complex modern grids from just outright failing? Because with the massive surge in renewable energy, our electrical grids have become, frankly, super fragile ecosystems. It's not just a simple one-way street from a coal plant to your house anymore. We're dealing with millions of moving parts and power flowing in every direction. How on earth do engineers predict cascading failures and stop major blackouts before they ever hit the real world?
Well, to unpack all that, we'll look at the Modern Grid Challenge, introduce you to DIgSILENT PowerFactory, check out its core simulation features, walk through building a grid model, and then wrap up with some real-world applications. Starting off with Section 1, the Modern Grid Challenge, specifically focusing on integrating renewables. The source material really highlights that injecting unpredictable power, like wind and solar, makes managing grid stability a massive, high-stakes puzzle. When fluctuating power hits a system that demands absolute perfect balance 24/7, well, the risk of instability just skyrockets. Engineers can't just cross their fingers and hope for the best here. They have to aggressively model and stress test everything virtually before a single physical wire is connected. Which brings us to Section 2, Meet DIgSILENT PowerFactory. It's essentially the digital crystal ball for engineers. So what is it? PowerFactory is a comprehensive software tool by DIgSILENT GmbH used for analyzing, simulating, and modeling electrical power systems. Honestly, think of it like a highly advanced flight simulator, but for grid operators. It lets them accurately predict how the system will behave and spot fatal flaws in a totally safe virtual space. Before a new solar farm goes live, it's meticulously modeled here, letting engineers push the entire network to its absolute limit without risking a real-world blackout. Moving right along to Section 3, Core Simulation Features. Let's see exactly how they stress test this infrastructure. This tool's massive versatility boils down to 4 core capabilities: load flow analysis, short circuit analysis, dynamic simulation, and renewable energy integration. It handles literally everything, from your normal daily operations to sudden catastrophic grid disturbances. Let's break down how these specific features actually stop a system collapse. First up, load flow analysis. This is basically the grid's routine health check. It determines the steady-state voltage levels, active and reactive power flows, and energy losses across the whole network. By crunching these numbers, engineers can ensure the grid is running efficiently and, most importantly, staying well within safe physical and thermal limits. I mean, you've got to definitively prove the baseline is stable before throwing any crazy external stress at it, right? But, what happens when things go really wrong, like a lightning strike or a downed transmission line? That's where short-circuit analysis comes in. Engineers can simulate severe events, single line-to-ground faults, line-to-line faults, or those massive three-phase faults. They blast these intense bursts of virtual fault current through the model just to see if the protective relays will trip in time or if the whole thing is going to go down like dominoes. And to actually survive those massive hits we just talked about, engineers rely on dynamic simulation. This guarantees the grid keeps its delicate synchronism. If a sudden shock causes a huge frequency drop, the network might just trip completely offline. So dynamic simulation tracks transient stability and frequency response over time. It lets engineers design automated controls that catch and stabilize the grid right before things cascade into total chaos. Let's jump to Section 4, Building a Grid Model. Let's explore how you actually build one of these complex virtual networks from scratch. You definitely can't just wing this. Building an accurate model requires a really strict sequence. First, you create your buses, generators, and loads. Second, you map out the intricate network topology connecting them all together. And third, you perform that baseline load flow analysis. Because, frankly, you cannot run advanced dynamic simulations on a model that hasn't been carefully parameterized and stabilized first. And when you're designing that topology, you aren't just dragging and dropping icons on a screen. You have to precisely define the exact mathematical characteristics. Buses act as the critical connection points, while you map out the real and reactive power limits of the generators supplying the system alongside the dynamic demand of the loads consuming it. By meticulously dialing in these parameters, the virtual model becomes a perfect mathematical twin of reality. Okay, so once this incredibly complex simulation is actually running, it spits out a massive volume of data. Thankfully, PowerFactory has amazing visualization tools to help engineers interpret voltage drops and overloads. Instead of just staring at endless spreadsheets of raw numbers, they get these visual heat maps and topological diagrams. They can spot dangerous anomalies instantly, which is exactly what allows them to optimize grid operations on the fly. Which brings us to our final section, real-world applications and the impact on our future. So why does all this matter outside the lab? Well, grid operators actively use this software for grid planning and expansion, renewable energy systems integration, and power system protection design. When regional power demand surges, they use this tool to safely plan out insanely expensive infrastructure upgrades. When a huge new wind farm goes up, they use it to synchronize it without crashing the network. It's basically the ultimate testing ground for the protective measures that keep our lights on. Now, the source material does point out a catch. There's a real trade-off here. All this high precision and system accuracy comes at the direct cost of a very steep learning curve and massive software complexity. You really need a profound understanding of advanced power system physics and numerical analysis to run this thing. But honestly, mastering this complex environment is totally non-negotiable for the engineers' tasks with upgrading and safeguarding our modern infrastructure. So, as we wrap up this explainer, next time you flip a light switch, will you wonder if a simulation run months ago is what kept your lights on today? It's pretty fascinating to realize there's this invisible, highly complex digital armor working relentlessly behind the scenes. Tools like DIgSILENT PowerFactory are quietly securing our sustainable energy future, making sure that no matter how chaotic the modern grid gets, reliable power remains an absolute certainty. Thanks for joining me today to explore the hidden systems powering